So these continental convergent plate boundaries, they form very large interior mountain ranges, so mountain ranges that are not along a coast. So where the Andes is an oceanic continental convergent plate boundary, which forms a coastal mountain range on the west coast of South America, Himalayas is a mountain range formed by continental collision, which forms a large interior mountain range. So the Appalachian Mountains running along the east coast of North America, they formed through this process. Whenever North America slammed into Africa during the formation of Pangaea, it was a continental convergent plate boundary which formed a large interior mountain range like the Himalayas. So if you were standing, say, in upstate New York 500 million years ago, it would have been similar to the Himalayas of today. Hotspots. Hotspots are these small, they form from these small pipe-like upwellings known as plumes in the mantle. So if we have the core mantle boundary and we have the lithosphere, the top of the lithosphere up here, these mantle plumes are these small pipe-like upwellings that eventually reach the top of the mantle and intersect with the lithosphere. Why they occur, we actually don't know. It's an area of active research. The hot mantle material rises up through them, the surface. And above them, because this hot mantle material is very warm under high pressures, as it rises, it decompresses. Remember that decompression melting causes the rock to partially melt. That melt rises to the surface and erupts and forms volcanism. We call that volcanism, due to this mantle plume, a hot spot. So as I mentioned, as the mantle material in the plume nears the surface, partial melting due to decompression melting occurs. And that melt rises to the surface and forms volcanism, which we call a hot spot. This is how some ocean islands form. And ocean islands that formed by hotspots are either active or extinct volcanoes. So the interesting thing about the mantle plumes that generate these hotspots is that the mantle plumes remain fairly stationary in the mantle, while the lithosphere is moving over top of them. So as a result, the volcanism that is produced in the lithosphere because of this mantle plume, it records the direction of plate motion. So for example, this volcano is now extinct. It was active whenever it was located over the mantle plume. As the lithosphere moved this direction, this volcano moved out from over top of the mantle plume, and the volcano went extinct. Currently, this section of the sphere is over the mantle plume, so active volcanism is here. So this is where the hot spot is. We have a animation that shows us this process. So here we have the oceanic crust in the uppermost part of the mantle. Together they make the oceanic lithosphere, with the asthenosphere below it, and this is the mantle plume, a small upwelling that has intersected with the bottom of the lithosphere. The lithosphere is moving, and decompression melting causes molten rock, which rises and results in volcanism, forming a hot spot. As the lithosphere continues to move, this volcano goes extinct, and new volcanism forms. And this process continues, repeats itself. And if you'll notice that once the volcanoes go extinct, that they actually begin to shrink and subside beneath the water eventually. And this is because whenever the volcano is active, you have eruption after eruption, which adds mass to the volcano. While erosion is removing mass from the volcano. But the rate of mass addition from the volcanism is greater than the rate of mass subtraction from the erosion, so the volcano grows. But whenever the volcano goes extinct, now you have only erosion, and so you have only the removal of material, so eventually the island shrinks, it becomes smaller, it's eroded away, and it sink beneath sea level. Okay. Hawaii is a poster child for this hotspot volcanism. So here are the Hawaiian Islands, the Big Island of Hawaii, Maui, Molokai, Oahu, and Kauai. And the only active volcanism in the Hawaiian Islands is in the Big Island of Hawaii. And it's in this area of the island. There's no volcanism over here, and actually the youngest volcano hasn't reached above sea level yet. And volcanism has occurred on the Big Island from 0.7 million years ago to present day. So this is the part of the lithosphere that's currently over the mantle plume where the hotspot is. In Maui, you see volcanism has occurred here between 0.7 and 1 million years ago. As you move further this way, Molokai, volcanism occurred here 1.3 to 1.8 million years ago. Oahu, 2.2 to 3.3 million years ago, and Kauai, 3.8 to 5.6 million years ago. So as we move in this direction, we see that the age of the volcanoes becomes older, and so this marks the direction in which the Pacific plate is moving. What this means, between 3.8 and 5.6 million years ago, this section of the lithosphere, or Hawaii, was located right here. And so this is the oldest volcanic island, or it's extinct now, of the Hawaiian Islands. Does that mean that this volcanism at this hotspot didn't begin until 5.6 million years ago? Well, remember that once the volcano goes extinct, they often shrink because of the erosion, and they become submerged. And you can see that there's a long line of extinct volcanoes in line with the Hawaiian Islands, and that line actually continues. It just takes a jog or a bend. And we call this line of extinct volcanoes along the seafloor, these are seamounts, and this is the Hawaiian chain of seamounts, and then this other segment is the Emperor chain of seamounts. So volcanism has been occurring at this hotspot for a very long time. For example, the island of Midway, still above sea level, volcanism occurred there 27 million years ago. So 27 million years ago, this part of the lithosphere was located right there. It's traveled this far in 27 million years. And here we have this volcanic island that went extinct 65 million years ago. So 65 million years ago, this was an active volcano located right there. So whenever this was active, the dinosaurs were still on the planet. And for all these older volcanoes, they were formed and active while dinosaurs were in their heyday. Older volcanism has been destroyed. It's been the lithosphere, which those extinct volcanoes were on, has been subducted to subduction zone. So we don't know how long volcanism has been occurring here, but it has been for quite some time. You might be wondering why this jog in the lithosphere occurs. It's thought that subduction initiated along a certain part of the edge of the Pacific Ocean basin. Whenever that new subduction zone initiated, it caused the direction of the Pacific plate to change. And so as that sudden change in direction of the Pacific plate caused this jog in the seamount chain with these extinct volcanoes. So in conclusion, the theory of plate tectonics provides us provides a picture of this actively cycling planet, and because of it, it has this ever-changing surface. And so with the single world ocean, on that surface, it is influenced by that ever-changing surface. So as the plates shift, new ocean basins are created, old ocean basins are destroyed, and all the while in between, those ocean basins are changing shape, shifting positions. So the state of the ocean is a very dynamic one. It's constantly changing, though it's very slow. We cannot perceive it with our own eyes by watching it. It nonetheless is occurring at a very slow but constant rate. So that's it for our lecture on earth structure and plate tectonics. If you have any questions, please email me, or better yet, post them on the questions board so that others can see them and see the answers to them. Thank you very much.